So this is a little bit more about differentiability from lesson 3.2. I wanted to go over a couple of things with you and discuss them a little bit further. So the things we need to know are how to determine where the derivative is going to fail. I do want to talk about how to take derivatives on the calculator. And then we're going to talk about the intermediate value theorem as it relates to derivatives. So when the derivative fails, there's four instances that we need to know. First is if there is a corner. And the big one on this are our absolute value functions, okay? They make a V and there's a corner. And at that corner, the derivatives will be different from the left hand and the right hand. So there is no derivative at a corner. Second is a cusp, which is very similar, but there's a little more curve to it. And the function would not be differentiable at that point. In fact, the book calls this an extreme corner. It's the same kind of idea that the right hand and the left hand limits are different for that, okay? Third is a vertical tangent. And the one that kind of comes to mind is a cube root function, which graphs like this. And you can see like at 0, the graph goes vertical. And so there is no derivative there as well. And then the fourth is a discontinuity, which kind of just makes sense. If there's no derivative, then there's no derivative. It's non-existent at a discontinuity. So like a jump discontinuity, there would be no derivative there because the limits from each side would be different. Okay, so those are our four instances. The easiest way to tell these is from a graph. So graphing is really super helpful. Now, most of the functions we're going to look at are differentiable wherever they're defined. And I want to pick out that phrase because that's really key there, okay? If you think about like rational functions, they have an asymptote. The domain is not defined at that asymptote. And so it sort of doesn't count in the differentiability because the function is still differentiable because that asymptote is not part of the domain. So the graph will be unbroken and smooth, even though it's broken up by that asymptote. That asymptote is not part of the domain, so the function is differentiable. So if we want to just look at this absolute value, I graphed it real quick here and find out where it is not differentiable. The best way to do this is to look at the graph and notice there's a corner. So the function is going to be non-differentiable at the point where x equals 2. Now, it's going to be differentiable everywhere else because these are all straight lines. They will all have derivatives. Until you get to that point where x equals 2, there will be no derivative. Now, the difference about this is that 2 is part of the domain of the function. It exists at x equals 2, the function does, but there's no derivative there. That's how this is kind of different than like the rational functions with the asymptotes, okay? So I kind of wanted to point that out. This is sort of new territory for us, and it relates to continuity. So we have a couple different theorems that we need to talk about as relating to differentiability and continuity. The first is that differentiability implies continuity, okay? If f has a derivative at a certain point, then f is continuous at that point. So for example, if f is a function and it has a derivative at x equals 3, then f is continuous at x equals 3. Now, the converse of that is not true. To say that if something is continuous, it has a derivative at every point, that is not true. An absolute value function, again, is continuous. However, it does not have a derivative at that corner. So we can go one way with this. We can say if it has a derivative, then it is continuous, but we can't go backwards and say if it is continuous, it has a derivative at every point, okay? Be very aware of that. Theorem 2 is the intermediate value theorem. So if A and B are any 2 points on an interval where f is differentiable, then f prime takes every value between f prime A and f prime B. We talked about this with functions. Now we're talking about it with derivatives, but the same idea is true. So if we have an interval where f is differentiable, then the derivative function will take on every value between the derivative value of A and the derivative value of B, okay? So let's dig into this a little bit farther. Theorem 1 says that if a derivative exists at a point in the domain, then the function is continuous at that point. So what we're doing is we are looking at the limit as x approaches a of f of x should be equal to f of a. All right? Which it kind of makes sense if you think about it. But what that translates to then is that the limit as x approaches a of f of x minus f of a, right, my brackets here, is going to be equal to 0. That's kind of maybe an easier way to look at that. Okay, so for example, if let's say we're going to figure this out with a function, we would want to kind of work it out. And the book gives a really nice sort of breakdown of the limit product rule and how to do this so that we can get 0. Okay, so that's kind of a process that we can follow every time to sort of prove this out. The second theorem is a little more interesting to wrap your head around, I guess. So given A and B are the endpoints of a continuous interval A to B. Now I use the word continuous there because we know that if it's continuous, then it should have that it should be continuous, that there should be no jumps or breaks or holes or anything, okay? Then every value between f prime of A and f prime of B is covered by the graph of f prime. In other words, there are no y values that are not covered if it is, and maybe I should have used the word differentiable instead of continuous. I'm using them interchangeably, and that's not necessarily true, but I'm sort of discounting all of those weird things that we just talked about, okay? The corners and the cusps and all of that. So if we have an interval, unless there is a cusp or a corner, the function is going to be continuous because it will have a derivative at every point. And then because there is a derivative at every point, there is a f prime value at every point. In other words, for every point of where the derivative is x, there's a y value between whatever the y values of the two endpoints are. That's kind of a weird one. I don't know that I'm explaining it super clearly. I hope that makes sense to you. If not, we can discuss it a little bit further when we're in person, but this is kind of an interesting one to wrap your head around, okay? So I would like you to work on page 114. I've got a couple of questions here for you, and I will put this on Schoology as well. I am going to post out a worked out answer key for you. That will happen later today. It will not be right away. But I just want you to try some of these, think about some of this, and we'll keep working with the derivative.